is Dr. Smith. We're going to be walking through the in-class problems that we worked today in class. This is covering interaction terms and adjusted R-squared. It's also got some review in there for quadratic terms and dummy variables as well. So just to let you know, this is some data that came out of a textbook that I use in one of my other classes. Basically, it has information on extramarital affairs. We've got 601 observations, and the dependent variable here is the number of affairs in the last 12 months. Then we've got a lot of independent variables such as the age of the individual, the years that they've been married, their education level, how they rate their marriage, how they rate their involvement in a religion, whether they're male or female, and whether they have kids or not. And so we'll just go ahead and dive in here to the questions. First is we're going to test the overall significance at the 5% level. So first, whenever you see the word test, okay, the word test should tell you, man, we're going to be doing a hypothesis test here. Anytime you're doing a hypothesis test, you care about p-values. So when you see the word test, the word p-value should be the next thing that comes in your head. Anytime we're testing the overall significance, right, you're testing the significance of the entire regression, what that means is that you're going to be using the f-test. This is the f-test of the regression. And specifically, its p-value, which is here under the significance of f. So that significance of f is the p-value for this f-test. Remember, this f-test is basically testing whether all the beta coefficients, except the intercept, all the beta coefficients, beta 1, beta 2, beta 3, beta 4, etc., are equal to 0. That's the null hypothesis of this f-test. And so the null is basically that nothing matters, right? It seems very sad null, but nothing matters. And then we're trying to disprove that. That's what we're trying to gather evidence for. And so we've gathered evidence, this data set, and by doing that, the p-value is really, really, really small. That's a 0 followed by 13 more zeros, and then finally a 1. So that's a really, really small p-value. And so we need to compare that p-value to our level of significance, which is 5%. Okay, and so in this case, since the p-value, that's the significance of f, is less than 5%, we reject the null that nothing matters, and the regression is significant. Okay? So, very straightforward. Just the regression is significant because the p-value is less than 5%. Okay, how does the number of years married affect the number of affairs someone will have on average? So, one of the things that I mentioned in class was we needed to add in if they've been married 10 years. Okay, I forgot to add that in the other day, so we'll add that in now. How does the number of years married affect the number of affairs someone will have on average if they've been married for 10 years? So we want to see basically going from year 10 to year 11, how will that impact? And so to do this, we need to use the slope. Okay, so the slope formula for someone for a variable that has a quadratic term. So a couple people missed that there was a quadratic term here. Anytime you see this underscore SQ, that's a quadratic term. That's years married squared. That's what the SQ stands for. And so, well, that's how I notate it. Different people might notate it differently, but this is how, when you're in my class, you'll know that you have a squared quadratic term here because I put that underscore SQ at the end of it. Okay, so anytime you're dealing with quadratic terms and you need to know the effect or how something affects something or the relationship or anything talking about, how X changing affects Y, we need to use this slope formula for the quadratic term. And remember that it is beta, let's see, linear, let's see, that doesn't like me today. Let's see, beta linear plus 2 times beta quad times x, right? That's our formula. And so plugging in this particular case, the slope is equal to beta linear, coming up here to the top, is on the years married, that's our linear term. So we'll come down here and plug that in. Plus 2 times beta quad, which is the negative one here. I'm lazy, I'm copying and pasting. Times, and our x in this case is years married, which in this case we know is 10. Okay, so we calculate that out. Let me grab a calculator real quick. So we do 0.2707 plus 2 times oh, come on, computer. Okay, I'm going to do this over here in Google. You can use your own calculator. Let's just grab this. Plug that in Google. And we get 0.1523. Ooh, it's got big. Okay. Let's bring that font size down a little bit. Whoa, just kidding. Well, let's fix that problem. Oh, come on. That's what I get for trying to do stuff late at night. Okay, so there's our answer. So that is the effect of someone if they've been married for 10 years. All right, now, is that result significant at the 5% level? So we come up here to the top, and we need to look at our two variables here, years married and years married squared. Years married is significant at the 5% level. Years married squared is not. Now, there's a more complicated way to do this. You would need to do an F-test. We haven't gotten to that in class yet, and we're not going to at this point. But there is a way to do a joint significance test of the two. For right now, since we don't know how to do that, we would just need to say something like, let's see, years married is significant at the 5% level, but years married squared is not significant at the 5% level. And that's fine, okay? Great. So, are men different than women when it comes to cheating? Test this hypothesis at the 10% level. So we come up here, we look at the male variable, right? Remember, this variable is comparing men to the category that's been left out, which is women. And so if we just look at the coefficient here, this coefficient says that men, on average, in this data set, cheated on average 0.1637 times more than the women did. Okay, but if we come over here to the p-value, again, remember it said test this at the 10% level. Test means we need to look at the p-value. The p-value is like 0.56. That's much bigger than 10%. That's like 56%. And so what this means is that at the 10% level, the male variable is insignificant, which means there's no evidence that in the population men cheat more than women. Okay. Part D. What is the predicted number of affairs we would expect from a 45-year-old man who has 12 years education, rates his marriage a 3 out of 5, has no kids, and rates his religious involvement as a 2 out of 5, and has been married for 10 years? So basically, this is going to be our y hat. Okay, so let me start an equation here. This is going to be, let's see. Okay, there's y hat is equal, and this is going to be, so we start off with our intercept, which is 5.542 plus, then we'll go to our next coefficient, which is age, which is negative 0.0452. So negative 0.0452 times the person's age, and they're 45, plus he has 12 years education. So let's go here and look at the education. Education is 0.013. So 0.013 times 12 years education, plus rates his marriage a 3 out of 5. So we come here and we look, marriage rating is negative 0.7149. So come back down here, 0.7149 times, he rated that a 3. Okay. Plus, has no kids. We don't need to worry about the kids. It's 0 times whatever the kids is, so we don't need to worry about that. Rates his religious involvement. So we can go up and look at religious involvement. It is negative 0.4798. So negative 0.4798 times, he rates it as a 2. And finally, he's been married for 10 years. So we go up and look for years married. Years married is 0.2707. So 0.2707 times 10. And then we also need to do the years married squared, which is negative 0.00592 times 10 squared, which is 100. Okay, this is our, and that's going to be equal to what our y hat is. So again, I'm going to use Google for this. So let's see, use this one. Actually, I'm going to go use Wolfram Alpha. So it'll handle that a little better. Put this over here. Copy this. Here's Wolfram Alpha. We'll see what that's equal to. And it's equal to 2.6747. So 2.6747. Okay. Which is equal to 2.6747. So we would expect someone based on this data, someone who has that particular set of demographics to, on average, have 2.67 affairs in the last 12 months. Okay. Let's see. E, what is the effect of years married on the number of affairs someone has for 10 years? We actually already did that. That's right here. Okay, so I'll just copy that down here. Okay. And we're going to do the exact same thing to calculate it for someone for 30. So for slope is equal to, and I'm just going to copy this, because now we're going to check this for someone who's been married for 30 years. Okay, let's see what that comes out to be. So we'll take this and we'll go plug it in our calculator, which I'm just using an online calculator to do this. You can just plug it directly into your calculator. And that comes out to be, whoops, just kidding. Negative 0.0845. So let's talk about these two differences, right? So looking at this, what does this mean? Well, this means someone who is married for 10 years and then they get another year of marriage. They move up to 11 years of marriage. We would expect the people who have 11 years of marriage to have slightly more affairs, 0.1523 affairs, more than the people who have 10 years. So going from 10 to 11 years, on average, increases the number of affairs that someone would have. But going from 30 to 31 years decreases the number of affairs that someone would have. So it looks like there comes a point where you've been married long enough, you're less likely to have affairs. It looks like you're likely to have more affairs when you're early in your marriage, and that slows down until it comes to a point where you're less likely to have affairs the longer that you're married. So that's what this next question wants to look at. And we want to say, okay, at what point does years of marriage have no effect, right? So what we're going to do is we're going to set this equation equal to 0, okay, and then we're going to solve it. So let's come down here, let's create a new equation here. And we're going to set our slope equal to 0. And then we want to solve this equation basically for x. At what level of x does this equation become 0? Okay, so what you're going to do is you're going to subtract both sides. So you're going to come here. Let me see if I can do this. So this leads to, I'm going to subtract 0.27 from both sides. So I end up with negative 0.2707 is equal to 2 times negative 0.00592 times x. Okay. Then I need to divide both sides by the 2 times negative 0.592. So we come up with, this leads us to x is equal to negative 0.02707 divided by 2 times negative 0.00592, close that. Okay, and then we just need to plug that into a calculator. So we'll come here and we'll just copy that. We'll go plug that in over here. And we get 2 point, that's not right. Let's see, hang on. Okay, I figured out my problem. This should not be 0.027, it should be just 0.27. That changes a good bit. And so with that in mind, we'll come back to our answer here. We'll change it in our calculator to fix that problem. And we find out 22.86 is the answer. So we'll just minimize this. And then so this is equal to 22.86. Okay, so what does that mean? That means after 22.86 years of being married, okay, so about almost 23 years of marriage, at that point it becomes less likely each year that you're going to have an affair, right? Someone would have an affair, okay? Basically, so up to that point, every year of marriage, you're more likely to have affairs. After 23 years of marriage, or at the 23 mark, basically every year after that, you're less likely to have affairs. So, there you go. Interesting data. So last thing, part F, calculate the adjusted R squared in the table. So we come up here, okay, so I have adjusted R squared here blanked out. So how do we actually calculate that? Okay, so let me see if I can get us a little space down here that I can type in. Let's see. All right, so calculate adjusted R squared. Let's create an equation here. So adjusted R squared is, let's see, so we've got adjusted R squared. Its formula is 1 minus R squared times n minus 1 divided by n minus k minus 1. Okay, that's our formula for this. Okay, so all we need to do is really plug into that. Okay, so let's plug into this equation. Okay, so we've got 1 minus, and let's go up here and get R squared. What is R squared in this equation? It's, let's say, 0.1308. Go down here, 0.1308 times n minus 1. Okay, n minus 1 is 600. And k in this case is 8. How do I know k is 8? Well, there's an 8 here. That's k, if you remember. Or I can come here and I can count the number of variables. So 1, 2, 3, 4, 5, 6, 7, 8. So k is 8. Okay, so either way, k is 8. N minus 1 is 600 because n is 601. So we'll come here and we'll do 600. Should actually do this in the equation, not outside of it. 600 divided by 601 minus 8 minus 1, which is 592. Okay? And that's going to be equal to, I'm just going to take that and plug that into my calculator, also known as Wolfram Alpha. By the way, if you guys don't use Wolfram Alpha, it's really nice. This comes out to be 0.119, let's say 0.1191. And that is your adjusted R squared. Okay? There you go. That's how you calculate it. Part 2. A different researcher is interested in determining the effects of men's wages and runs a regression using hourly wage as the dependent variable. So this is all men we're looking at here. For independent variables, 3 dummy variables were used: union, which denotes whether the worker is a member of a union; black, which denotes if the worker is black; and Hispanic, which denotes if the worker is Hispanic. Other variables were education experience, both in years, of the worker, and 2 interaction terms, each interacting education with the 2 race dummy variables. So we've got 2 interaction terms here at the bottom, which will play into what we're doing. The basic output from Excel is seen below. So here's the part that we actually care about. 1, what is the effect on hourly wage of being in a union? Is this a significant result? So what this says is, let's see, being in a union raises wages by 0.66, we'll say $9. Right? How do I know this is dollars? Right? Where do I get dollars from? Remember, our dependent variable here is hourly wage. Hourly wage you measure in dollars, right? So being in a union raises your hourly wage. So I'll go ahead and put in hourly wage here. Hourly wages by $0.669, or basically almost 67 cents an hour. But, the reason I'm writing but here, so we look at the p-value. P-value is 30%. So, but this is insignificant at the 10% level. So also at the 5% and 1% levels. And so there's no relationship between being in a union and a change in hourly wage in the population. And I guess I should say there's no evidence of a relationship between being in a union and a change in your hourly wage in the population. Okay, so in the sample there was, but it doesn't look like in the population that there's no evidence for a relationship there. Okay, 2, even though there are 3 races in this data, okay, white, black, and Hispanic, why are only 2 dummy variables, black and Hispanic, included in the regression? There's a lot of ways to answer this. First, if you remember, when we were first talking about dummy variables, we talked about the idea that if you have 3 dummy variables, for those of you working on the project, you see this. When you have multiple dummy variables, you always have to leave out one. The regression cannot run if you include all the dummy variables because of something called perfect collinearity. It just literally, the math does not work. The math breaks down if you have all the dummy variables included. So there's no way to run the regression when all the dummy variables are included. So I'm going to write it this way. So because of perfect collinearity, thank you, Microsoft Word, for fixing that. So perfect collinearity, we cannot include all of the dummy variables in the regression. We must always leave out one of the categories. Okay. Part C. What is the impact of education on hourly wage if the worker is white? What about black and Hispanic? Is the impact of education on hourly wage for black and Hispanic workers significantly different than that of the white workers at the 5% level? All right, how do we do that? Well, this is where these interaction terms are going to be playing in, okay? Because this education term here, this is the return to education for everyone, okay? Specifically, that's the return to education for white individuals, okay? This education black variable here, this variable is kind of the extra effect for if you're black. And the education Hispanic variable here is the extra effect if you're Hispanic, okay? So, coming up here, the effect of education on wage if you're white is 1.49, we'll say 1.498. 1.498. So almost $1.50 an hour. So what this means, I'll put a dollar sign in front of this. Oops. Is basically $1.50. So what does that mean? That means if you're white and you get another year of education, it raises your pay by $1.50 an hour. Okay, so that's a really big effect. All right. So that's kind of that's interesting. Okay, so the return to education for someone who is white is about $1.50 per year of education. Okay, now if you're black, the effect of education on wage is that original dollar, say $4.50-ish, right? But plus the extra effect if you're black, which in this case is a negative effect, so 0.488, we'll say 489 to round it, okay? So which is equal to, and we'll just take this, just grab a regular calculator because I can use a regular calculator for this. So 1.498 minus 0.489, which is basically 1.009. So basically $1.01. So if you're black, the effect of education on your wage is basically $1. Okay, so if you're white, it's about $1.50. If you're black, one more year of education raises your pay by $1. Okay, so you can see how this interaction term changes the effect of education depending on the race variable, the race category that you're in. Okay. Finally, if you're Hispanic, the effect of education on hourly wage is that main education 1.498 plus the extra effect for Hispanic, which is negative 0.594. Okay, which is equal to, let me grab my calculator here. So 1.498 minus 0.594, which is 0.904. So if you're Hispanic, this is saying one more year of education raises your pay by about 90 cents. Okay, so we have three different effects of education on your pay, and it depends on what race you are. So if you're white, your one more year of education raises your pay by $1.50. If you're black, one more year of education raises your pay by about $1. And if you're Hispanic, one more year of education raises your pay by about 90 cents. So they're all still positive effects, right? But they are, in this case, they're all positive effects. The negative numbers here are showing you the difference from the white effect, the one that we left out. Okay, so with that in mind, now let's answer the next part of this question. Are any of those significant at the 5% level? Okay, so I'm going to start a new line here to answer that. So we come up here and we look, and education is obviously very significant. The p-value is very, very small. Okay, so in this case, that's significant. The question is, are black or Hispanic workers significantly different? So to come down to answer that question, these interaction terms are showing us the difference, okay, between that race and the white effect, okay? And so if we look at the difference here between black and white workers, that p-value is actually 0.25, so that's insignificant. So what we could say is that there's actually no significant difference between the effect of education on hourly wage between white and black workers. So while it's showing a difference in the coefficient, that there's not enough evidence to say that actually exists in the population. Okay? However, there is a significant difference between the effect of education on hourly wage between white and Hispanic workers. Why is that? Well, we come over here and look, and the p-value on the difference between white and Hispanic is 0.04, which is less than the 5% level. So because the p-value is less than our significance level, we say that's significant. Okay, that's it. That's how you work all these problems. Your test will be very, very similar to this. Feel free to watch this as many times as you need. You can always email me or call me if you have any questions. Thanks, guys.